All right, so welcome to the last class. Let's see, let's go over some just little kind of exam logistics just to make sure we get that done. So, our exam has been scheduled for Thursday, December 11th. So I guess that's a week tomorrow. And it starts at 8:30. Unfortunately, I didn't schedule it. I get the schedule from administrators just like you do. So it's going to be in Art 106, if I wrote that down correct. And so what can you bring? You can bring a formula sheet, 8.5 by 11, regular letter size piece of paper. You can write whatever you want on it. I print something in micro font. It's totally up to you. You do what you like. You can use both sides of it. You can bring a calculator. I haven't made the exam, so I don't know exactly what it's going to look like. I doubt that there's going to be a lot of punching numbers into a calculator, but by all means, bring one. The only restriction is that it can't go online and it can't communicate wirelessly with other devices. If you have your favorite graphing calculator, that's fine too. Okay, some people like to have headphones to cancel noise. That's fine, except they just can't be electronic. So no electronic devices with you other than your calculator. I said that I would post assignment 6 solutions, the assignment that's not going to be collected and graded. I still intend to do that. I got to get through some other things first, but I'm hoping that, maybe by sometime on Friday night, those will be on the course website. So what we will cover is we've covered essentially all of chapters 1, 2, and 3, and chapter 4, we've done 95% of it. So we're gonna finish up to 4.4.2 in chapter 4. And so the section after that is called addition of angular momentum. So we're not covering that. It's not going to be on the final exam. So the cutoff is up to and including 4.4.2. What I am going to try to do, and so this is just a guideline. It's not like a rigid, this is exactly how it's going to break down, but I'm going to try to make it about 60 to 65% material since the midterm. And so that's going to be essentially chapters 3 and 4. And then the rest, the 30 to 40% that's remaining, will come from chapters 1 and 2. Okay, so that's the plan. Any questions about any of those kind of logistical things? All right, not seeing anything. Okay, so what we were doing last time is we were talking about a spin in a magnetic field. And what we started doing was saying, well, if we had a charged sphere and we rotated that sphere about some axis that goes through that sphere, then we would have moving current. And moving charge. And that moving charge is a current. Current is a source of magnetic field. And so a spinning charged object would have like a dipole moment. The electron is kind of a structureless point, or maybe it's better to think of it as like a probability amplitude spread over space. There's nothing physically spinning, but in analogy with that classical view, electrons do have a spin angular momentum and an associated angular moment. And what we did is we ended up figuring out the energy of a magnetic moment in a static magnetic field. And it ended up being a dot product between the magnetic moment and the applied static field. If we choose our static fields to be along the z-axis, then what that does is it pulls out the z component of the spin. And we ended up writing down this Hamiltonian for the energy of a spin in a static magnetic field. And you can actually see immediately that this is Hermitian. If I was to transpose that little 2 by 2 matrix, I'd get the same matrix back. Also, there's no complex quantities in there, so taking the complex conjugate would do nothing. And so this is a Hermitian Hamiltonian, a Hermitian operator. That means we should expect to get real eigenvalues. Okay, we did write down the eigenfunctions of the Hamiltonian. Because the only operator in the Hamiltonian is Sz, it's the same eigenfunctions that we had for Sz and S squared. There's the spin-up eigenfunction, which is just a 1, 0 column matrix, and then a spin-down one, which has a 0, 1 column matrix. And when we act on those states with our Hamiltonian, we get the eigenvalues, and they were the same, but with opposite signs. And so the idea is that when you have a spin in 0 magnetic field, the spin up and spin down states have the same energy. They're degenerate. When we apply the static field and we set some value for B0, we split those energy levels in proportion to B naught. Okay, and so one of them is a little bit lower in energy and one's a little bit higher in energy. So what where we ended last time is we said, okay, let's make a general spin state. Chi0 is some superposition of the spin up and spin down eigenstates for the Sz operator. And so we imagine that we prepare this state at some time t equals 0, and then we allow the system to evolve. And the time evolution of each of the eigenstates is going to be an e to the I times the energy times time over h bar. That energy for us in our Hamiltonian was omega b naught. Where was it? Here it is. Sorry, the energy was gamma b naught h bar over 2. So when we put that into, oh God, such a lag. When we put that in here, I'm going to define omega naught as gamma b naught. The h bar over h bar cancels, and we get these little phase factors that multiply our coefficients a and b. If we wanted to, we could factor out the phase factor for the a coefficient, and that leaves us with an a b times e to the minus I omega naught t. This little prefactor out front's not going to matter generally, because if I was to calculate some kind of expectation value, it's going to involve chi times its conjugate, and that's going to cancel this little phase factor. And what we get is one state that is stable, and then the other one that has its phase evolving, and it's rotating at a frequency omega naught. All right, so that's where we got to last time. And so what I want to do is we're actually not going to do too much new today. We're just going to interpret what we've already worked out for the most part. Okay, so for our normalized state, we're going to require that the coefficients A and B, if we take their absolute square and add them up, that has to be 1. That's a conservation of probability kind of idea. But we've already decided that A and B have to be real if they're going to be part of the eigenstate of the Hamiltonian. So we could say, since H is Hermitian, H chi must return real eigenvalues. Okay, and so that implies that A and B are going to be real. And so the condition for normalization becomes a little simpler. And that is just that we just take the regular square of A and B and add them up, we have to get 1. But there's a nice way to do this. There's a nice way to guarantee that A squared plus B squared is 1. And that is to think of it in terms of like a circle. A circle, if it has a constant radius of 1, is going to just be x squared plus y squared is equal to 1. And we can do that by the following. We are free to express the coefficients of this two-level system as A is cos. I'm going to write it as alpha over 2, and B is sine alpha over 2. So clearly, if I square these two, I'm going to get cos squared plus sine squared. That's going to add up to 1, regardless of what we put in for alpha. The other nice thing about this is, as I vary alpha, I can vary this cos alpha over 2 between 0 and 1. So I can have the weight A shift from 0 to 1 for how aligned my initial state was with, say, the spin-up state. And conversely, we can vary how aligned we are with the spin-down state. We'll actually come up with a bit of a geometrical interpretation of what alpha is in just a few minutes. So here, alpha characterizes how aligned our spin state chi is with the spin up and spin down eigenstates. If alpha is 0, we're perfectly aligned with the spin up state. If alpha is, say, what do we need? Pi. If I put in pi, then we're perfectly aligned with the spin down state. Okay. So what we're going to do is I'm just going to rewrite this chi of t, the time evolution of our general spin state, in terms of this alpha parameterization of A and B. Okay, so chi of t is going to be, okay, let's see. We have an A, which we're going to write as cos alpha over 2. And then I'll use the form on the left. So it's e to the I omega naught t over 2. And then for B, we have sine alpha over 2, e to the minus I omega naught t over 2, like so. All right. Okay, good. So that's the time evolution of our spin state. What I want to do is I want to calculate some expectation values. So let's find the expectation value of Sx. So this calculation is going to help us with our kind of geometrical interpretation of what the state looks like. We will explicitly do the Sx expectation value, but then we can do in the same exact method the expectation values for Sy and Sz, but we'll just write those results down. All right. So what's nice about this matrix representation of our operators and eigenstates is that all of these expectation values just reduce to matrix multiplication. We don't have to do all of the integrals of chi star times Sx times chi integrated over whatever the variable is. The reason we don't have to do that is because when we set up our matrix representation of the operators, we pre-computed all those expectation values. And so it greatly simplifies a lot of these calculations. All right. So let's see. We first have to produce our adjoint of the spin state. So we transpose and complex conjugate the state that we've already worked out. And I'm going to move this over just to give ourselves a little more space here. All right. So we're going to transpose. So our column becomes a row, and we get cos alpha by 2 e to the, we have to take the complex conjugate, so we get a minus I omega naught t by 2. And then we get sine alpha by 2 e to the plus I omega naught t over 2. All right, and then we need our spin operator. So we wrote those down last time. It has a prefactor of h bar by 2, and then there's a 2 by 2 matrix. For Sx, the 2 by 2 matrix was 0, 1, 1, 0. And then we just have to finally copy down our column matrix. So that's cos alpha by 2, e to the I omega naught t by 2, sine alpha by 2, e to the minus I omega naught t by 2. Okay, and so now we just have to do the matrix multiplication. Cos alpha by 2 e to the minus I omega naught t by 2 sine alpha by 2 e to the plus I omega naught t by 2. Okay, so we'll first do this multiplication. This one's the Sx matrix. It's like the opposite of identity almost. So identity would be 1, 1, 0, 0. So we have our diagonals flipped. And so what that does is it flips the order of the states here. So 0 times the cos plus 1 times the sine puts the sine on top. So we're going to get a sine alpha by 2 e to the minus I omega naught t by 2. And then 1 times the cosine term plus 0 times the sine term. So the cosine term ends up on the bottom. E to the I omega naught t by 2. Okay, so now we have 1 by 2 row matrix times a 2 by 1 column matrix, and that's going to give us just the number. And that's what we want. It's the expectation value for some operator. Turns out to be the x component of the spin. Okay, so we have our h bar by 2 out front. And let's see, we're going to get cos times sine. So we'll have a cos alpha by 2 times sine alpha by 2. And let's see, the exponentials are not going to cancel. So we're going to end up with an e to the minus I omega naught t. It's not t by 2 because we get these two factors that we have to add up, and that eliminates that 1/2. All right. And then we'll get a plus. Again, we're going to get cos times sine, and the exponentials are again going to combine. It's just, instead of e to the minus I whatever, we have e to the plus I. So we get cos alpha by 2 sine alpha by 2 e to the plus I omega naught t. So, all right. So we could simplify this quite a bit, actually. There's a trig identity where the product of cos and sine with the same argument is equivalent to 1/2 sine alpha. And so this is also 1/2 sine alpha. Okay. So let's see, what does that leave us with? It's h bar over 2, 1/2 sine alpha, I can factor out. And then we get e to the minus I omega naught t plus e to the plus I omega naught t. Well, that's quite nice because e to the ix plus e to the minus ix is 2 cos x. So this is 2 cos omega naught t. And we can cancel that 1/2 with that 2. And we get a pretty nice little expression here. The expectation value for the x component of the spin is h bar by 2 sine alpha cos omega naught t. So this cos omega naught t is obviously like an oscillation. And so it looks like the expectation value of the x component of the spin is going to increase, reach some maximum, go through 0, go negative, and it's just going to keep doing that over and over. It's going to be this periodic oscillation. If you did the exact same thing for the y and z components, you would find that sy expectation value is going to be h bar over 2. You could probably guess what's going to happen. We're going to get a cosine. Sorry, no, you won't. Sorry. I said you could guess, and apparently I can't. So we're going to get a sine alpha. And it's this one that changes. It's going to be a sine omega naught t. So it likewise oscillates in time, but because we have cos and sine, they oscillate out of phase. All right. There's one other little wrinkle, and if you go and do this calculation, you'll actually pick up a negative sign. All right. And then it's the SZ. I was getting ahead of myself. The SZ is the one that's going to have the cos alpha. And in fact, it will not have a oscillating part. It's going to be constant in time. And you can understand why, actually, because if we go back to this top line here, if I put in the SZ operator, it's going to be a diagonal matrix 1, 0, 0, -1. And so because we have the normal diagonal, it's not going to swap the positions of the column vector. And so that means when I do this multiplication, this exponential is going to multiply with that one, and they're going to cancel. So that's the technical reason or the mathematical reason why it doesn't cancel. Okay, good. Anyways, these are some important results, and we're going to try to interpret them. Okay, so let's try to draw a picture here. And so I want to keep that on the screen while I draw my picture. So let's see if we can do this. So I'm going to have a z-axis here. And let's see, I'll make my y-axis over here and x over here. X, y, z. All right. Now, for our spin 1/2 particles, the spin vector s has to be 1/2. Can I get this to be straight? Okay, let's make it straight. Okay, so I'm going to draw a spin 1/2, and I'll draw it something like this. So this is our spin vector. It has a length of h bar by 2, and I'm going to draw an angle alpha with respect to the z-axis. Okay, so the first thing we could imagine doing is projecting down into the xy plane. And so if I do that, There's our projection down into the XY plane, and I will draw this vector in the XY plane. So this is Y. Okay. So this is the side that is, let's see, opposite of alpha. So that should be sine alpha down here. So what we should have here is h bar by 2, the length of our vector, times sine alpha. Okay. Now, if we imagine, say, t equals 0, if I put in t equals 0 here, Sx will be h bar over 2 sine alpha cos of 0. But cos of 0 is 1. So this full length will be in the x direction at t equals 0. But then as time evolves, we rotate away from the x-axis. And how much we rotate away from the x-axis is specified by omega naught t. It's our phase. It's the evolution of the phase of our spin eigenstates. Okay, and so once omega naught t becomes pi by 2, then we'll be fully aligned with the y-axis. Our Sx expectation value will vanish, and Sy will have a value of, oh, I guess I've drawn this the wrong way if it's going. Okay, yes, let's fix that. When we get to pi by 2, we will be in the other direction. So I should draw my omega naught t as rotating around. Let's see if I can draw this a little better. So we're going to go around and around and around, and we're going to come back over here. So this is omega naught t. Okay, good. So when we get to pi by 2, we'll be in this direction, and that will give us the negative value for Sy. All right. So let's continue these little projections here. So we have one here, and we've got one over here. All right. So what we might be interested in is the length here, which is this x component of our spin. So it's going to be h bar over 2 sine alpha, and it's going to be cosine of omega naught t. H bar over 2 sine alpha cos omega naught t. Likewise, the y component is here, and that's going to be h bar over 2 sine of alpha sine of omega naught t, and then we'll just need our little negative sign here. All right. Then finally, the last one we have is, let's see, I'll probably copy this. And let's see if I place that over here. I'm going to need to give myself a bit of space here. Okay, I'm just going to get rid of that box. Okay, so I'll extend my z-axis here a little bit. And this is going to be the z component. This is going to be h bar by 2 cos of alpha. So this is our sz expectation value. This is our sx expectation value. And this is our sy. And so if you look at this picture, what's going to happen is this blue vector is just going to keep rotating around the z-axis forever. And it's going to maintain a constant z component of the spin, but the x and y components will be evolving all the time. The length of those two, sx squared plus sy squared, will be constant, but the direction will be constantly changing. And so this is called spin precession. The spin precesses around the static field that you created. So our static field is along the z-axis. Okay, good. And so you can see where that interpretation of alpha is. The alpha is the angle that the spin makes with the applied field. So the spin S precesses about the knot, which is aligned with the z-axis. It precesses with a constant sz, while the components of s in the xy plane constantly change. But they change in a predictable way. All right. And so this is exactly like when if anyone has taken the third year mechanics course, the advanced mechanics, physics 328, you'll probably talk about the precession of a top. So if you spin a top and it makes some angle with the gravitational field, it'll precess around that gravitational field, which is vertical on the surface of the Earth. And so all of the physics of our spin precession is very much aligned or parallel to the precession of a physical top that's rotating. Okay. So this picture of a spin vector rotating about B is a mental model that appeals to the classical analog of a precessing top. However, for a quantum spin, nothing is physically rotating in space. Right? Our electron is not a simple little tiny ball that has a magnetic moment pointing in some direction and it can physically spin. What's actually precessing is the phase of the components of our general spin state, of the coefficients in front of the eigenstates of the Hamiltonian. The Z component of the spin is a superposition of the spin up, pi plus, and spin down, pi minus, eigenstates. And so let's see what happens if we do this. So chi is equal to A of t, chi plus B of t pi minus, where we've just worked out what these look like. A of t is cos alpha over 2, e to the I omega naught t over 2, and b of t is sine alpha over 2, e to the minus I omega naught t over 2. So notice that if I was to take the absolute square of each of a of t and b of t, the exponentials will go away, and I'll get cos squared plus sine squared. So I still get 1 when I add the squares of a of t and b of t, the absolute squares, and so we still have our probability conservation. So notice that a of t squared is cos squared alpha over 2. B of t absolute squared is sine squared alpha over 2. And these are constant. So therefore, if you really could set this up where you had an isolated spin making some angle alpha with respect to an applied magnetic field, these squared amplitudes would just be constant. Our spin vector would just precess indefinitely with that same frequency omega naught. So an isolated spin precesses at frequency omega naught with a constant angle alpha with respect to our vector B, our applied field, and it'll do this indefinitely. So what I want to emphasize is what is actually precessing is the relative phase of the probability amplitude of the two-state system. In fact, we can see it right here. Our A coefficient, the coefficient of the spin-up eigenstate, precesses at frequency plus, or with a phase of plus omega naught t over 2. And the coefficient of the spin-down state precesses with the same phase, but in opposite direction. And so they're getting more and more out of phase as time goes along. Once we get to, where this one is plus pi and this one's minus pi, then they will come and overlap again and they'll pass each other. Okay, so one state's phase precesses as e to the plus I omega naught t over 2, and the other as e to the minus I omega naught t over 2. Therefore, their phase difference evolves as e to the I omega naught t without the divide by 2, because we get half in one direction and half in the other direction. Okay, so I want to connect this to something real. And so we kind of, I think I mentioned it in the last class about MRI and NMR. And so let me just point out just briefly, the same effect occurs in NMR, except that the spin, except that we have a huge collection of spins in a lattice. Okay. Uh, so what they try to do in NMR or MRI is they try to prepare the system so that every single spin in the lattice starts out in the same, where is it? In the same, where did you write it down? In the same chi-0 state. So we start the system with the same coefficients A and B for every single spin in the system. And I'm not going to talk about the details, but we can do that with certain RF pulses, where the pulses are tuned to the frequency difference between the spin up and spin down states. And so if you can do this, you can prepare all of your spins in the same state, then the time evolution is the same for all of them. So they evolve synchronously. And so now you have a huge number of spins precessing all the same, and you get a large effective magnetic moment that precesses in the XY plane, and you can detect that. Or it doesn't have to be the XY plane, you can set it up with any alpha you want. In NMR, they usually will try to make alpha 90 degrees so that you're spinning in the XY plane, and you can actually detect that rotating magnetic moment. All right. The other thing that's different about NMR, let's go back to our Hamiltonian and our energies. Where are the energies? Oh, there they are. Okay, good. So our energy is going to be determined by gamma and B naught. That's our omega naught. So that's our spin up and our spin down states. What happens in NMR is that the spins are rotating, but they're also coupled to the lattice. And the lattice is a messy environment. It's sucking energy out of the precessing spin system. And as you suck energy out of that precessing spin system, what happens is alpha gets smaller and smaller and smaller, and your spin vector starts to realign with the local magnetic field so that you enter into the lower energy state. And so suppose gamma is positive, which it is for protons, then you all enter into this E plus state, which is the lower energy state, and that aligns the spin with the local magnetic field. And so as it's precessing, it tilts back up, and that is called T1. It's the time for the spin to relax back to its equilibrium. So the lattice dissipates energy from the precessing spins, which causes alpha to decrease, aligning S with the static field. All right. So I think the last thing I want to do is I just want to talk about the Stern-Gerlach experiment. And so this is something that you probably already talked about in Physics 200. And so we'll do it again. Maybe it'll be a slightly, different presentation. We'll find out. This is in Griffiths. It's example 4.4. Stern-Gerlach experiment. This is the experiment which initially confirmed all of these ideas that we've been talking about this quantization, specifically of the Z component of our spin. So if we have a spin 1/2 particle, the Z component can only be plus h bar by 2 or minus h bar by 2. There's nothing in between. If you had a spin 1 system, then the Z component could be minus h bar by 2, 0, plus h bar. So yeah, probably plus h bar 0 and minus h bar. So you get 2s plus 1 states for the Z component of your spin. So if s is 1/2, 2s is 1, plus 1 is 2. All right. So I'm first going to draw the experimental geometry. What we're going to imagine is a beam of spin 1/2 particles. And we're going to make them neutral, so they're not going to be electrons. What was actually used in the original experiment, I think, was silver atoms. So this is a beam of neutral atoms. I'm pretty sure silver is what was used with a spin 1/2. Okay, and we're going to force this beam of atoms to go through a magnet. And so I'm going to try to draw a magnet, but I'm going to draw it in a little bit of a funny way. I'm going to draw the magnet as being a little bit asymmetric. And the only reason I'm doing that is because you'll see why in a second. It turns out that we're going to need our magnet to be not uniform. There has to be some non-uniformity to the field. And so we'll have a bottom pole of our magnet, something like this. Okay, and so these are our electromagnets maybe. So this is a non-uniform electromagnet. Okay, it's an electromagnet, so it's some kind of like windings of coil, and then we pass current through that coil, and it creates the magnetic field. And if we turn the current off, we can turn the field off. And so that will be important too. And just to give some sense, let me suppose that this field looks, oh, that's not what I wanted. Let me suppose that the field looks something like this. So I'm going to try to draw it non-uniform. So these field lines kind of curve a little bit. Okay. So we'll continue this drawing in a second. We're going to add some stuff to it. So we have to consider the force on a magnetic dipole in a non-uniform magnetic field. Okay, so in general, if I have some potential energy, I can deduce the force from that. It is minus du ds. I don't know, it's not responding. Okay. Let's see what happens if let's suppose I close this. All right. Okay, stopped broadcasting. Okay, so let's see if we can get this going again. Aha, so I've lost my connection. That's nice. So let's leave the meeting and let's see if we can reconnect. Let's see. Do I have a internet connection? Okay. So, um, you are not connected to the internet. Oh, okay, that's nice. I was connected. Okay. All right, I think we're coming back. Okay, good. So here's a potential energy. If I take a derivative of potential energy along some direction S, that gives me the force in direction S. In general, we could write the force vector as minus the gradient of the potential energy. All right, but last time we showed that U is equal to minus, U is equal to minus mu dot B. And so maybe we'll just stop here just for a second and understand why is it that a non-uniform field was required. We're going to end up taking the gradient of this thing. And so what I want is when I take the gradient of the magnetic field, I want that to be not zero. If B was constant or uniform, then when I took that spatial gradient, this will disappear and we'll get no force. So the gradient is required so we get a non-zero force. Okay, so F is going to be the gradient of this. The minus signs will cancel. And so we have the gradient of mu dot B. All right. Okay. So we want to consider a beam of neutral spin 1/2 particles traveling along the y direction. Okay, so I said we would add some stuff to our picture, so let's do that. I'm going to make this the y direction, and then this will be our z direction. So our field is going to have a strong component along the z direction, and then we'll have our x direction as being like perpendicular to the screen. Okay, good. Then the beam passes through a inhomogeneous magnetic field. Okay, so B is equal to minus. So we have to make up a field. So I'm just going to make one up that will demonstrate the effect that we want. So it's going to be, I don't like alpha because we already used alpha for something. Okay. Well, okay. I'll stick with the notation Griffiths uses. So it'll have an x component given by alpha times x, where alpha, let me just at least put an alpha 1 here. Alpha is some coefficient that has the right unit. So it's in Tesla per meters or something. So when I multiply by x, then I get Tesla. Okay. And then we're going to have a z component. The z component is going to be B naught. B naught's going to be a big constant. But then we'll put in some other factor here, alpha 1 times z. And then here's k hat. Okay. So B naught is strong. And alpha 1 characterizes the deviation from a uniform field. Okay, so now, since we've picked some parameterization of our magnetic field, we can evaluate this dot product. Mu, we said, was gamma S last time, and then we're going to take the dot product with this magnetic field. Okay, so the first term is going to select the X component. So this is going to become a gamma SX, and then we'll have a minus, let's see, gamma alpha 1 X SX plus. Then we take the dot product with the Z component. So this is going to become gamma SZ. So we pick up a gamma again. We're going to get a B naught plus alpha Z, and then we need our SZ. Okay. Then finally, we can take the gradient of this dot product. It's going to be pretty easy, actually, because the d by dx is just going to only act on this term, and it's going to kill the x. The d by dz, it's going to kill b naught completely because there is no z dependence here. It's constant. So it'll just take this alpha z and turn it into just alpha. Okay. So therefore, f is the gradient of mu dot b. It's going to be, let's see, I should put an alpha 1 on my alpha. So we get gamma alpha 1 from both. We'll get a minus sx in the x direction, and we'll get a plus sz in the z direction. All right. Now, we've already discussed that if we put a spin in a magnetic field, it'll start precessing around that magnetic field. So if our field is predominantly in the z direction, all of these spins are precessing about the z-axis. And so that means in the x direction, we're constantly rotating. So the x component of the spin is changing all the time. If we average over many periods of that oscillation, the force that we get is going to average to 0. It's only the sz, which is constant, that has a non-zero average. So we've already seen that the spins precess about B naught K, which is the dominant direction of our magnetic field. So the Sx component of the force averages to 0. Okay, so the net effect of the force is purely along the z direction. Okay, so the z component of the force is going to be what? Gamma alpha 1 sz. But sz can only be, for a spin 1/2 particle, it can only be plus h bar by 2 or minus h bar by 2. And so there's this 1 over 2. Sorry. Yeah, so we'll put h bar here and then ms, where ms is going to be plus or minus 1/2 for s is equal to 1/2. So therefore, particles with spin up experience a force that is equal and opposite to that of the spin down particles. Okay, so what I want to do is look at this drawing again. And so let's imagine that our spin 1/2 particles enter this field. They start seeing a non-uniform field. The gradient has non-zero factors. The components that are in the XY plane average away, and we have only a Z component of that force. If you're a spin up particle, maybe you're going to be deflected in one direction. And then if you're a spin down particle, you're going to be deflected in another direction. And so this could be, say, spin up, and this could be spin down. And so if you imagine that you have some kind of detector plate on this side, you can see where your particles hit this plate. So this is going to be a detector plate. And so you could get these little plates that will leave a little mark wherever a particle hits them. And so people did this experiment, and I'm going to find kind of the original. Here it is. So let's move this up. And there we go. So this is actual data from the original Stern-Gerlach experiment. Data from original Stern-Gerlach experiments. Okay, so what we're seeing on the left is this black line is where all the silver particles hit their detector screen. This one on the left was taken with the magnetic field turned off. We have, say, an electromagnet. We turn off the current, it generates no field. So this is the B equals 0 case. And so there's no deflection of particle beam. All right, and then we turn on the field and you see it splits. And if it was the case that the Z component of our spin 1/2 particles could be anything, then what we would expect to see is just a smooth, kind of blurry, fat line here. Because if we prepare a beam of particles that are all independent of one another, their spins could be any random orientation, then some will see a big force, some will see a small force, some will see a negative force, and you just get some blurry blob. But that's not what we see. We see that there's clearly a gap in the middle where no particles hit. And so we only get particles in one of two locations, and that's the quantization of the Z component of the spin of our particles. And so this is the B not equal to 0 case. Particles hit in only one of two locations corresponding to Sz is equal to plus h bar by 2 and Sz is equal to minus h bar by 2. And so it's right here. Out here at the edges, it's probably, I'm just speculating now. It's probably that the beam is fairly wide and parts of the beam don't go through the region where there is a strong field, or maybe where the gradient of that field is weak, and so they don't get deflected. So what we're really focused on is the part in the middle where that gap is quite large. Okay, and so that's the Stern-Gerlach experiment. So I've got some examples here, but these were examples that I was just going to write out the solutions for. I don't want to just rush through them in the last 5 minutes, so I carefully, and I will post them to the course website, but they're all going to be problems on working with I hope you learned something. I hope you enjoyed it a little bit at least. Good luck with your exams. If you have any questions during the exam period, like in the next week, I will be probably on campus on working days. You can also send me an email and we can converse that way if necessary. All right. Thank you very much, and we'll see you next week.